All right, welcome back. We're going to continue with lesson 2 today. And this lesson will be about measurements, significant figures, and using dimensional analysis, which is a method to do calculations in a single line. And what you'll want to have done before watching this video is just to make sure that you understand how to make use of your scientific calculator, and you can do the conversions for scientific notation. We'll practice that with this lesson as well. So if you're not an expert at it yet, it's not a big deal. So let's start with discussing the difference between precision and accuracy. And then I'll go into the rules for reporting significant figures. And we'll then get into the major chunk of this lesson, which will be on using dimensional analysis. And we'll have a significant amount of practice problems that we can do for this one. All right, so the first thing that we need to discuss is what the definition of accuracy is and what the definition of precision is, and how they relate and compare to each other when we're making measurements in chemistry. We can make use of a dartboard and think about the bullseye as being the center of the dartboard. The center of the dartboard is the true number, the most accurate portion of the dartboard. And if we get the darts in the middle, we're going to consider that to be accurate. And then if we have several darts that we throw, and they're all clustered around the same spot, we would then call that to be precise. And we can see in the third one here, we have high precision but low accuracy. And then on the second one, we have high accuracy but low precision. And in the first one, we have both high accuracy and high precision. Now, when we make any type of measurement, it's difficult to have complete accuracy, but there are a few experiments that we can do that have complete accuracy or zero error, and that's when we count numbers. So the counting of objects is something that we could do exactly. But besides that, most things that we're going to have some amount of error in our measurements. Or I would say some inherent uncertainty. Now, what are some objects that we can count? Well, let's list a couple of them. Maybe there's 12 eggs in a carton. Or if we were to open up that carton of eggs and we count them, we're like, oh, we immediately see that one's missing. There are roughly 60 students in this class as of my recording of this video. Well, exactly as the recording of this video. So that's how many I'm expecting there to be. And then this was something I looked up, and I thought this was interesting. So the United States, of course we know, has 50 states. But additionally, it contains one federal district. So that's Washington, D.C. It contains five unincorporated territories. If I could spell. 9 minor outlying islands and 326 Indian reservations. So these are all things that you can count exactly. All right. Now, we'll define the accuracy of our measurement as how close it is to the actual value. And so the concentric rings represent our degrees of certainty. The further we get away from that center bullseye, the less accurate the throw is. And one thing that we can think about is, one property we can think of is density. And the density of an object is intrinsic to the property that to the sample that we're measuring. So if we have a pure sample of gold, it should measure as 19.32 grams per cubic centimeter. And that is something that is irrelevant of where the gold came from. And when we go to measure it, we might get a value that's less than that, 18.58 grams per cubic centimeter. So a density, we can see here, is a compound unit. It's the mass per volume of the object. And when our measured value is less than the true value, or the expected value, then our accuracy is considered to be low. The possible reasons for this inaccuracy could be a number of things, but these are some things I thought of. Improper calibration. So maybe we didn't calibrate our scale. We might have the incorrect technique. Or we have a sample that's been adulterated. Perhaps it's not pure gold, but there's some silver or another material that's mixed in with it. When we go to report this value, it's often easier to present it as a percentage error. And knowing how to write the percentage error correctly is important, and what that exactly means. So we'll take the average of all the values that we measured. So say we took density of gold and measured it 3 times, and we got 18.58. That would be our average value. And then we can subtract the true value, which in this case would be 19.32, divide it by 19.32, and then multiply it by 100. And that would give us our percentage error. So in this example, that would be 18.58 minus 19.32 divided by 19.32 times 100, which would be, put it back in normal mode, negative 3.83%. So a negative 3.83% error. And again, anything besides counting objects are going to have some inherent error to them. To determine what the actual true, accepted, or standard value is, we might make use of a standard textbook, such as the CRC Handbook of Chemistry and Physics. A lot of the standard values are recorded in something along those lines. Let's see if this link will work for me. So Boise State pays for access to this handbook here. So here's what it looks like when we pull it up. Say we want to look up a property of density. Let's say density here. So physical chemistry data. We could just simply type in density and we'll find it. Aha, okay. So let's say gold. And then we can find that the density of gold is 19.3 grams per cubic centimeter. Here's some other properties of gold. We have its melting point, its boiling point, its heat capacity, thermal capacity, and so on. And it shows here, this is presented in a variety of different tables here. I think I was looking for the density table originally. And if we want to show all rows, so we can see a variety of different densities here. So density is given by the symbol rho. So the density of aluminum is 2.377 grams per cubic centimeter. And then the slash here is Guggenheim notation. That's just referring to the units for this density. MP is at its melting point. And then there's a variety of different elements here. We got a variety of different densities. And so if you measure the density of an object, you might be able to determine what it's made out of. But if it's not a pure substance, which we'll talk about in the next lesson, it might not be super obvious what it is. But it can. That is just one property we can measure. Now, one side note here is that these values in this table and in all tables that we measure are not absolute truths, because science is constantly being improved. The equipment that we're using is changing with time. Hence why there's 114 editions, or 104 editions of this text of this book put out. These values can change with time, and they do. You can also find other reference manuals like the Particle Data Group. This is a really interesting set of information you can find for measurements on particles. So if we're looking at the properties of a proton is a type of baryon, and the first one that's listed here is P, that's the proton, and here are all the up-to-date properties on the proton. So the mass of the proton in terms of atomic units, in terms of mass energy value. There's a lot of really interesting things we can find from here, but this is outside the scope of our class. This would be if you were in a physics class. Right, we'd probably stick to this book for now. So let's go on and talk a little bit more about precision. So accuracy was what we just talked about. Precision is, again, how close our repeated measurements are to each other. That means how sensitive our measuring instrument is when it's used. Do I need to take a variety of different values before I'm convinced that I have the correct value? Or can I just make one or two measurements and feel comfortable about that? It's really nice when we have a high precision instrument, but high precision instruments can also lead to us thinking we have the right value when we actually don't. They might cluster around each other and we haven't calibrated it properly. Now, that's essentially the difference between the two. One way we can look at how higher precision is through the use of a scale. Scales will typically write it out in a digital format, so it'll say like 0.000 when you go to start the measurement, and that'll tell us that we can make our measurements out to 3 decimal places. And you're going to get a lot of practice with this with the accompanying lab that goes along with this lecture. Now, for the density of gold, if we were to measure one of the properties and we got it to 18.583 versus 18.58, it might look like those are the same number, but this one here is more precise than the other measurement because it has an extra degree of certainty to it, indicating that we have higher precision. So precision appears when we make a measurement or we write a measurement out as how many decimal places we can report it out to. So when we were looking at this table I just looked at, we have these values that are written out to like 3 or 4 decimal points. The one I just closed, pull this up again, you can see that these measurements here are recorded out to very, very high precision. So the mass of the proton is known to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 decimal points. So that's very high confidence that we have on that. Now, anytime we make a measurement with the human eye, one thing that we'll note is that we can make an additional guess between the markings that are given. And we'll learn about this in our lab. But if we have a Griffin beaker, which is a type of glassware that's calibrated to deliver a certain volume, it will have markings for 100 mil, approximately every 10 milliliters. So we have down here at the bottom, it's hard to see, but it should be 20. So at the very bottom would be 0. So 20, 30, 40, 50, 60, 70, 80. And then the markings for 80 and 100 aren't listed. So a Griffin beaker is not very precise. It's more used for, just collecting liquid that we're going to then pour into a more precise instrument for measuring volume. But these are all types of glassware I'm going to show you that are used for containing volumes. And let's think about what the cost is on something that's not very precise versus something that is more precise with increments of 1 milliliter, which would be like your graduated cylinder, versus something that is even more precise than that, which would be like a Class A burette, which unfortunately we're not able to ship in the kits. But if you go on to Take Chem 112 lab in person, you can use a burette in class and get practice with a very high precision instrument. And let's think about what the difference in cost between these three instruments would be. Well, this one here I'll tell you is $6.75 as last I looked it up. And then if we have something that has higher precision, so measurements every 1 milliliter. Now, because they're every 1 milliliter, we can actually make a guess in between those markings. So we can actually make a guess out to 0.1 with this. The cost of this Class B is $53.75. So roughly 10 times as much. And then the Class A burette is, you want to make a guess? See how much you think it is? So if you said $530, you're a little high, but it's $381 for a single burette. And these are very delicate instruments, so you want to be careful because this jet here at the very bottom can break really easily, and then you're left with a useless burette. Now, there's some other types of volumetric flaskware that is calibrated to contain a certain volume, and there's a marking here. It's hard to see, but this marking is where 100 milliliters exactly are in this volumetric. And this is really useful for when we're preparing a solution. We want to have it exactly equal to 100 milliliters, and we need to have a low tolerance in this volume. So the cost of this instrument is roughly $100. It's $90. And then we have another type of volumetric pipette, and if we look at the tolerance here, this tolerance is a little bit less, but it's a really easy way for drawing up a liquid of around 100 milliliters. And these two are approximately the same cost. The tolerance on this is just a little bit less, but still it's a more delicate instrument. So they do cost a lot of money. You can get an estimate of how much an instrument is going to cost by its tolerance, by its precision. There is one other type of volumetric flask, not volumetric flask, but flask that contains volumes. It's called the Erlenmeyer flask. It may have a component here that connects to a vacuum, but these are never for using to measure a volume. Because they're sloped, it's hard. You'll see here it says approximate volume. They're more used for titrations, which is when you are trying to neutralize a solution that's acidic or basic, or for recrystallization when you are trying to purify a substance. And then if you are growing cells, you might be using it to prepare a culture of that cell. So you'll see Erlenmeyer flasks a lot in the lab, but it's best to make use of one of these other types of instruments for making your measurements. Now that we have a little bit of an understanding of, and this is $11 approximately, of how measurements can be, can differ depending on the instruments we have, we can understand the concept of significant figures. So the higher the precision of the instrument, the more decimal points out that we can record. Now, anytime we report out a lot of decimal points, this is something we should think of as significant. And we always want to indicate this in our scientific notebook when we publish our results. And anytime that we're going to be doing calculations in this class, especially with our online homework system, it's going to be looking for you to report the correct number of significant figures. So it's important that you understand the different rules that I'm going to be talking about. And one thing I want to harp on is that we can only be precise as our least precise measurement. So if we make a measurement of mass and a measurement of volume to find the density, we can only be as precise as the least precise of the two. So if our measurement of the volume is less precise, which would typically be the case, then we can only be precise to whatever that volume measurement was. So let's look at a couple examples here. So if I measure the mass of a post-1983 US penny, and it records as 2.5 grams with a kitchen balance, and then I use an analytical balance or a jewelry balance for more precision, we might see that the scale will rate it as 2.500. The first instrument is precise out to 2 sig figs, and the second instrument is precise out to 4 sig figs. Whenever we record this number in our notebook, we have to record each digit the scale gives us. So even though in math class we would round this number to 2.5 and truncate the trailing zeros, in chemistry we're going to always want to keep every value that the instrument reports out to us, especially if it's a digital scale. This last number is going to kind of fluctuate depending on how much wind there is, but we want to report out every digit that's on that scale. All right, and the number of digits that are significant are the sig figs. And here are the rules that we need to know, and I would recommend practicing these rules here. So the first one is all non-zero digits that are in a number are significant. That means numbers 1 through 9 are significant. Second rule is that zeros between non-zero digits are significant. Any sandwiched zeros. Leading zeros are never significant even after a decimal point. And I'll give some examples of that in a sec, but leading zeros are the numbers that come at the beginning. Trailing zeros are only significant if they are after a decimal point. So we have these zeros here that occur after the decimal point, 2.500. So those are significant. But there is going to be a couple examples where, like say for example, 250. That last zero is not after a decimal point, so it may not be significant. It could be, but it's best to report all your values in scientific notation so we prevent ambiguity. So make sure that if you use scientific notation, you do it correctly, and this will allow you to prevent any ambiguity in trailing zeros. And then the last rule is that defined conversion factors and counted numbers are considered exact, and they have an infinite number of significant figures. Oops. Defined conversion factors. So for example, 1 inch equals 2.54 centimeters. That's not 3 sig figs. That's an infinite number. It's an exact number. And then 12 eggs or 60 students, those are considered exact. And they're counted, those because they're counted numbers. All right, so let's do a couple of examples of this. And when we do these examples, you might pause the video here and then try to answer it on your own and see if you're correct. So the population of the United States is 333,290,000. And I also want you to think about, what sig fig rules apply. So first, how many sig figs are there in this number? And then what sig fig rules apply? All right, so when we look at this, we have a total of 9 digits. 5 of them are non-zero. And then we have 4 trailing zeros. Now, those 4 trailing zeros are before a decimal point. There is no decimal point. If there was one, it would be listed here. So these may or may not be significant. And oftentimes when we make a population estimate, we don't know exactly how many people there are. Even though it may be something that we're counting with a census, the number of people that are coming in and out of the country varies on a day-to-day basis, and we might not have an accurate count as to how many people there are, especially with this many. That's an approximate number. In this case, I would say that there's 5 sig figs. Just the ones that are non-zero here, because these trailing zeros are before, not after a decimal. So rules 1 and 4 apply here. If we wanted to report this a little bit more accurately, it would probably be best to use scientific notation. And we could write 3.3329 times 10 to the 8th power, yes. All right, here's another example, 2,408 joules. Well, in this one we have 4 values. We have 3 non-zero digits, and we have a 0 that's sandwiched. It's between non-zero digits. And so in this case, all 4 of these digits are significant. So we have 4 sig figs. Rules 1 and 2 are applying here. Okay, and then here I have the mass of an electron. The mass of an electron is really, really small. We could rewrite this in terms of scientific notation if we did that. And oftentimes I'll group these zeros like it is in the textbook in groups of 3, so it's easy to count. So we have 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. And then we got to go one more to move the decimal point, so 31. So there's, so if we divided 9.11 by 10 31 times, that would be the same as writing 9.11 times 10 to the negative 31 kilograms. And what we see here is we have a whole bunch of leading zeros. Now those leading zeros are never significant, even after decimal points. So these 30 zeros right here have no bearance on the significance of this measurement. So in this case, there are only 3 sig figs, despite how many digits are listed there. This would be rules 1 and 3. And then this last number here is how many pages there are in our textbook. Now, it seems like a lot. Well, that's because we are this textbook goes through Chem 112 as well. So roughly pages 1 through 500 and I don't know. I think we're gonna get through chapter 14. We're probably not gonna get into chapter 15 all that much, just a little bit of it, but roughly the first 500 pages or so. Now in this case, there's 4 non-zero digits, so you might think that there's 4 sig figs, but in this case, this is a counted number. I just looked at the number of pages in this book, and that's how many there are. So this would be an exact number. So that's just rule 5. All right. So knowing how to make use of significant figures is really helpful. There are also going to be rules here for when we use them in calculations. So anytime we add, subtract, multiply, divide two numbers that have sig figs, we need to make sure that we express the final numerical result correctly. Let's start with multiplication and division because it's just a little bit easier. The calculated result should not be expressed to more significant figures than the factor that has the least number of significant figures. Let's start with a simple equation, such as the potential energy of a snowball that's at the top of a hill. So potential energy can be represented by the mass times the acceleration due to gravity times the height of the hill. The higher that the snowball is, the more potential energy it has. And it depends on also its mass. So the larger the mass it is. If we moved this to a different planet, the accelerational the acceleration due to gravity would change as well. Now, here we have the mass of a snowball. It's 2.5 times 10 to the negative 2 kilograms. So roughly 25 grams. We have a gravitational acceleration constant on average as 9.81 meters per second squared. And the height of the hill is 21 meters. When we go to do this calculation, we have 3 values that are multiplied by each other. So 2.5 times 10 to the negative second times 9.81 times, just 9.81. And I'm going to write actually our units in here as well. Times the height is 21 meters. Let's go ahead and do the calculation. So we have 2.5 e to the negative second times 9.81 times 21. And our value on the calculator gives us 5.15025. Now, we don't need to write all those values because, what was it, 025? And we shouldn't write down all those values because that would be too many significant figures. So it should be expressed to the factor with the least number. Well, we were multiplying 3 numbers. The mass and the height are also both reported to 2 sig figs. So our final value should be truncated to 2 sig figs. What we need to do is we'll truncate the second digit, which is 5.1. However, this third digit, the one after the value that's being truncated, is 5 or greater. So we should write this as 5.2. And then we need to write all of the units. So we have kilograms, we have meters, and we also have meters here as well. So these become meters squared, and then seconds to the negative 2. So we have kilograms, times meters squared per second squared. These units are best expressed as joules. So that we could also write as 5.2 joules of energy, potential energy. There's a different rule when we do addition and subtraction. The result of the addition or subtraction should have the same number of decimal places as the number with the fewest decimal places. So not the factor with the least number of sig figs, but the number with the least number of decimal places. Let's sum together the mass of an apple, an orange, and a kernel of popcorn. Before we do that, I just want to just add this here. Note rounding rule. All right, so an apple typically weighs around 125 grams. An orange weighs a little bit more, about 145 grams. And then a popcorn kernel is really small. It's about 0.4 grams. And when we add these all together, we're going to find that the total mass would be, well, we'll start down here is like 0.4, right? And then we'll add the 5s together. We'll get a 0. Carry the 10, giving us a 7 and a 2. So 270.4 grams. And that would be how you would add that in math class. But the kind of interesting thing here is the precision of the popcorn kernel is higher than the precision of the apple and the orange that is measured. So really, we don't want to report the mass as 270.4. We want to report it as 270. Because the apple and the orange have the least number. So we'll truncate it right there. All right, so 270 grams. And probably the best way to write this would be in scientific notation. So 2.70 times 10 to the second, because we're multiplying by 10 twice, grams. We could also write it in terms of kilograms, 0.270 kilograms. We could also write it like this too, 270 grams. That is sometimes what we'll see. We'll just have a decimal point there. That helps us indicate that this last value here is significant. We know it to the ones digit, not just the tens digit. All right, then what if we wanted to subtract a value? Let's take one like this, for example, 2,796.8 kilojoules, and we subtract 2,795 kilojoules from it. When we go to do this calculation, we can just use our calculator here. We can do 2,796.8, subtract 2,795, and we get 1.8, right? Well, the answer is not 1.8. Why is it not 1.8? Because our least precise measurement is right here, and it ends at the ones place. Our most precise ends at the 10th place. So in this case, we can only be precise to the value with the fewest decimal places. So we can only be precise to the ones place. Now this number here needs to be, we need to round it. Okay, so we're going to look to the first insignificant digit, which would be the decimal point. That number is 5 or greater. So this should be reported as 2 kilojoules. Just 2. Not 2.0, just 2 kilojoules. And one other thing you might notice from like this one up above, when I'm doing this calculation, 2.5 times 10 to the negative second times 9.81 times 21, and I got this value as 5.15025, then I truncated it. That's what you should always do for your calculations, is do all of the calculations and then look at the final answer to trim it. Because what will happen is you'll end up introducing rounding errors if you do it where you're kind of truncating your significant figures as you go along. So it's best to perform all the calculations to extra sig figs. The textbook and a lot of the calculations I've done, if you just include at least one more sig fig, that's usually best. So say, for example, you have a measurement that's out to 3 sig figs, and then you're looking in a table and you want to find a reference value, and that reference value is listed out to 8 digits. You only need 4. So get usually to like 2 extra sig figs, like maybe like one extra would be good. All right, so here we are getting to the most important part of this lesson, and it's how to make use of chemical calculations involving both scientific notation and the correct number of significant figures. Here are a couple notes when you're doing dimensional analysis, this method. This method is going to help you cancel out units. So whenever you perform a dimensional analysis, it will give you the units that you seek in the end. You may need to use the reciprocal of the conversion factor that you're given. So if you are given a value, given a conversion factor, you might need to flip it. It's worthwhile to plan how you're going to do your conversions before you start actually carrying them out. And the homework platform we're going to use is going to help you prepare and practice these skills. There's a link here on how to use active chemistry for dimensional analysis. This is going to be kind of like what it looks like. It's going to, our homework platform is going to have a problem for us to solve. It'll say something along the lines of convert this specific volume to a different unit using Olin metric system. And you'll have a starting box, and then you'll have these fraction bars, and then you can add fraction bars, and you can drag numbers, and there's a whole bunch of different answer choices, and it's going to really force you to learn it properly. And you'll see here it'll show you how you can cancel out units as you go along. So anything that's in the top will be canceled out in the bottom, and then whatever units are left over will be the correct value that you want. So in this case, 6.14 liters to milliliters. We need to know that there's 1,000 milliliters in a liter, or we could also say 10 to the negative 3 milliliters, or liters in 1 milliliter. So let's practice this dimensional analysis technique, and you'll understand a little bit more about how to use this. And then in the textbook also goes into a lot of detail in this. There are also going to be some units that we have that have units on the top and bottom. These are known as compound units. Density and speed are examples of these. And you often need to deal with both of them or one of them. When you use unit conversions that are squared or cubed, you'll also need to square or cube the conversion factor number. So when we convert from cubic meters to cubic centimeters, for example, that would require us to cube that number. And then after we've fully worked the analysis, we'll want to multiply all the numbers that are on the top, divide all the numbers that are on the bottom, and we can ignore all of the ones. If we multiply or divide by 1, it doesn't change our answer. And these are problems I found in the textbook that are really good for practicing these skills. And so I have a number of problems here. As with a lot of my videos, you can definitely pause this, practice these, and then see what my explanation is going to be. And that'll help you, I think, in the long run. So let's go ahead and start with this first one here. And I want to convert 1.259 times 10 to the third joules to kilojoules. You could go back to my lesson 1, and we can find the conversion factors for the prefixes. That's what we're going to need to look at. So you might have taken some notes and written these down, or maybe you have like a little cheat sheet here that you're starting to build. So kilogram or kilojoules, that would mean that you have 10 to the third joules. So the way to read this is a multiple of the base unit. So let's go back here. What we might want to write down is that when we have 1 kilojoule, that's equivalent to 1,000 joules, or 10 to the third joules. Let's write it like that for now. So this unit here, 10 to the third, is always going to be, these numbers here are always going to be with the base unit, okay? So when we do our conversion here, we'll start by writing the value that's given, 1.259 times 10 to the third joules. We'll write a multiplication sign, and then we'll write a fraction bar. Then what we want to do is make use of this conversion factor and place whatever unit that we want to cancel on the bottom with its unit. So 10 to the with its value. So 10 to the third joules is on the bottom, and then 1 kilojoule is on the top. And then we can see here that if we have a number on the numerator and a unit on the denominator, those units will cancel out, and we'll end up with the correct value. So 10 to the third divided by 10 to the third, that's like 10 to the 3 minus 3, or 10 to the 0, which is just 1. So these actually end up getting canceled out. And then we're left with, our answer is just 1.259 kilojoules. One thing to make note of is that all conversion factors are equivalent to 1. And anytime that we're doing dimensional analysis, essentially all we're doing is multiplying through by 1 in a fancy way. And this results in no change to the value that we're working with. We're just changing the units. Sometimes we are doing multiplications in there as well, but usually what we're just doing is we're converting. That's why we're able to write this as a fraction. So 1 kilojoule equals 10 to the third joules. 1 kilojoule over 10 to the third, that equals 1, because everything is equal to 1. Let's do a little bit more difficult problem here. I have 5.5 capital M capital J to lowercase k capital J. All right, so why did I say it like that? Well, because you need to know what these prefixes stand for. Capital M is mega, and then the J is joule. That's the unit of energy. So I have 5.5 megajoules, and I want to convert it to kilojoules. All right, there are two ways to do this problem. The first method is to make use of two conversion factor prefixes. So we go back here, and mega, that's 10 to the 6th, and then kilo is 10 to the third. All right, so 1 megajoule is equal to 10 to the sixth joules. And then the other one is 1 kilojoule is equal to 10 to the third joules. All right, so there we have two of our conversion factors. What we're going to do next is use both of them. So we'll set up two different fractions. Fraction 1, fraction 2, equals sign, and then we want to convert this to kilojoules. You can always set up your plan kind of along this line where you have, you need to make use of two conversion factors, and you know what your final units need to be. What we're going to do first is we're going to convert megajoules to joules. So we'll put 1 megajoule is equal to 10 to the sixth joules. And then at that point, if we were to stop the calculation, we would have 5.5 million joules. And then we can convert joules to kilojoules. So here I have this conversion factor. We'll make use of 10 to the third joules on the bottom and 1 kilojoule on top. We'll see here that megajoules cancel, joules cancel, and we're left with the unit that we want, which is kilojoules. When we want to simplify this, 10 to the sixth divided by 10 to the third. Well, if you remember our exponent rules from lesson 1, that's just 10 to the third power. So we have our final answer. It's 5.5 times 10 to the third kilojoules. Now, this is method 1. What's method 2? Well, usually when we're converting between two prefixes, it's kind of extra work for us to first convert to joules and then to convert back to another prefix. So we can make use of the absolute exponential distance between these two prefixes. What does that mean? So let me draw this out for us. Here I'm going to draw kind of like a number line. And one end here, we're going to have 1 joule. And then we're going to have 1 kilojoule. And then 1 megajoule. 1 joule is the same as 1 times 10 to the 0. 1 kilojoule is the same as 1 times 10 to the third. And 1 mega is 1 times 10 to the sixth. And then if we look at the exponents here, we have 0, 3, and 6. Now, the absolute exponential distance is the difference between these exponent values. So we have 6 and 3. The difference between those is 3. 6 minus 3 is 3. If we did 3 minus 6, we'd get negative 3. But the absolute exponential distance is just the positive value. And we can always place the 1 with the larger unit and the absolute exponential distance with the smaller unit. So let me show you what that means. We take 5.5 megajoules, and we have megajoules on the bottom, and we want to convert directly to kilojoules. Well, here we going to put the 1 with the larger unit, and then the absolute exponential distance here with the smaller unit. And if we do that, we're always going to get the right value. And in this case, it's the same. It's 5.5 times 10 to the third kilojoules. Now, this is a little different than this method up above. So there's two methods here I'm showing you, so make sure you know the difference between the two. The first method makes use of the prefixes, where the exponential value goes with the base prefix, just the value with no prefix, like joules, grams, meters, seconds. The second value looks at the absolute exponential distance between the two prefixes, places that exponential prefix with the smaller unit and the one with the larger unit. This is a shorthand method, and there's this website called chemteam.info, which is where I came up with this method. I learned it from this website, and they talk about it here under metric prefixes. They talk about the conversion here, actually under this one here. They talk about converting between two values that have different units, and this comes up, somewhat often. So now let's just kind of stick with the first method for now. Okay, so the second method is like a shortcut, but we'll stick with the first method, and let's do a couple more problems. So this one here is going to be looking at what did I call these? Just values that are cubed or squared. So here I have 2.0 cubic meters, and I want to convert this to meters. That's not right. To milliliters. Can't convert a volume to a mass. I knew that was wrong when I wrote it down. All right, so how do I convert between a cubic meter and a milliliter? Well, we can go back to lesson 1 to remember this. We have down here, 1 milliliter is the same as a cubic centimeter. So maybe we want to first convert cubic meters to cubic centimeters, and then use this as a definition, because 1 milliliter is equal to 1 cubic centimeter. We can also find this under the volume information here, but it's actually not as good. So let's go back and let's just use that as conversion here. So we have 2.0 cubic meters. And let's write down those conversion factors. So I said 1 cubic meter is equal to how many cubic centimeters? Well, let's first look at the conversion between meters and centimeters. So let's see, 1 meter is equal to 10 to the negative second centimeters. Or we could write that there is 100 centimeters in 1 meter. Okay, whoop, I got this wrong. Yeah, okay, so there's 10 to the negative second meters in 1 centimeter, or we could write 100 centimeters in 1 meter. Those are equivalent. And then the other thing I talked about was that there's 1 milliliter in 1 cubic centimeter. All right, so the first thing we want to do is convert cubic meters to cubic centimeters. And then once we've done that, we can convert cubic centimeters to milliliters. And then we'll get our answer in terms of milliliters, which is what we want. Now in this example here, we want to cube this conversion factor. So if I take 10 to the negative second, I need to cube this. And this one here is just going to be 1. So 1 cubed is the same as 1. And then we can do the same thing on the bottom here. Well, this one actually is just a 1-to-1. So we just look over here at our conversion factors. So we have, for 1 cubic centimeter, we'll have 1 milliliter. All right, so how do I simplify this? Well, I have 10 to the negative second cubed. And our exponent rule for this is we have to multiply the 2. So that's the same as saying 10 to the negative sixth. So we can kind of simplify this. So let's go ahead and simplify it. 1 cubed is 1. This is 10 to the negative 6th. And then this is just 1. So what's 2.0 divided by 10 to the negative 6th? Well, another exponent rule I told us is that 1 over 10 to the negative 6 is going to be equal to 10 to the positive 6th, like this. So we can also write this as 2.0 cubic meters times 10 to the positive 6th. Okay, so we have our final answer is 2.0 times 10 to the 6th milliliters. Okay, so I'm ignoring the units here, but the units, if we look at it, they cancel out here to just give us milliliters. I often try to avoid using the calculator on certain problems, but you can also use the calculator to solve any of these. So if we were to go and do 2.0 divided by 10 to the negative second cubed, what we'd want to do is use some parentheses. So 10 to the negative second and we'll get our answer is 2 million. Example 4 looks at a mass that's in pounds, and we want to convert it to kilograms. In this case, we're using a imperial unit, the pound, and we need to know how many kilograms there are in 1 pound. We could use the direct conversion right here. So 1 pound is equal to 0.45359 kilograms. By the way, these are all on the back page of your textbook. 0.45359. Okay, so we can take 175 pounds. I'll use this like curly L here so I know. I'm talking about an L. And then here, well, we want to put the 1 pound on the bottom, and because we want to cancel out that unit. And then on the top, it's just the value that's written here. And this one, I'm going to use my calculator. And we're going to get 79.37825. And we want to remember to apply our significant figures rule. So in this case, we have this, which we're going to treat not as an exact number. It is an approximate, but there's 5 sig figs here. But this one only has 3 sig figs. So this refers to how many sig figs there are, whereas this one has 5. So the multiplication rule says that we're going to truncate it to the same number of sig figs that the least precise measurement has, which is the pounds. So here we're going to truncate to the 3 sig figs, and that'll be 79.4 kilograms, because we need to round up, because the 4th digit, first insignificant digit, is 5 or greater. How many minutes does it take for light to travel from the sun to the earth, given that the sun is about 93 million miles from the earth? Now, this problem can be pretty difficult if you don't know what the speed of light is. So let's go and let's find what the speed of light is. I don't think I've given it to us yet, so we might need to go find a reference. Let's find... let's see. So on this website, what this would be under is physical constants. So speed of light here is listed as 299,792,458 meters per second, and it's given as an exact value. Okay, so let's copy down this value. And equals c. C is the speed of light. All right, so this here is going to be our conversion factor. It's going to tell us how many meters that light travels per second. We're also going to need to know how many minutes there are in a second. There's 60 minutes. Sorry, there's 60 seconds in 1 minute. And there are, so we'll need to know that conversion factor as well. And then what we can do is we're always going to start with the value that's given. Okay, so we'll have 93 million miles. So million here is referring to times 10 to the 6th power. So I could write this as 93 million, like this. And then that's million miles. Okay, so we're going to need to know another conversion factor here. We need to know how many meters there are in a mile. So we'll go back to lesson 1. We'll find that in one so in 1 mile, there's 1.6093 kilometers. What was it again? 1.6093. And then we need to know our prefix here for kilometers. So 1 kilometer is equal to 10 to the 3rd meters. So here we have conversion factor 1, conversion factor 2, conversion factor 3, conversion factor 4. 4 conversion vectors. The first two, 1 and 2, are exact. Conversion factor 4 is also exact. Conversion factor 3, I believe, is an approximate. But here we have 93 million miles. So our number of sig figs is only equal to 2 here. 2 sig figs. So we're going to round everything at the end to 2 sig figs. Now I'm going to rewrite 93 million miles in terms of scientific notation. So we'll do 93 million miles. So a million is 10 to the 6th. This is, but this one would be 10 to the 7th. And what we're going to need to do is figure out what order we want to use these conversion factors in. All right, so we need to make use of all 4 of them. And then what we're wanting to do is get our answer in terms of minutes. We can start by taking the miles here and converting the miles to kilometers. So 1 mile is 1.6093 kilometer. 1 kilometer is equal to 10 to the 3rd meters. And then meters, we can convert to seconds using the speed of light. Now, this number here goes with wherever the meters is. Okay, so we can write it as 299,792. Now, in this case here, we can actually truncate some of these numbers. Like, we don't need all of these. We can rewrite the speed of light as 2.99, let's say 8, times 10 to the 3, 6, 7, 8. Let's do it like this. It's often unnecessary for us to use all those digits there. It's just going to be rounded off in the end anyways. So 2.998 times 10 to the 8th meters per second. So the second, so it's per 1 second. That goes on top. That's how this becomes our conversion factor. And then how many minutes are there? Well, in 60 seconds, there's 1 minute. So here is all the work that we need to do to convert between the distance from the sun to the earth and how many minutes it takes for light to reach us. And let's plug all this in the calculator. So what I would do is I would write this all in scientific notation. So 9.3 times 10 to the 7th. And then I'm going to multiply it by 1.6093. Now there's I'm going to multiply all the numbers that are on top. So the next number is 10 to the 3rd. So 10 to the 3rd. And then anything that's on the bottom I need to divide. So I'll do divide by 2.998. And then in this case, I need to make use of the this exponent here, e. Otherwise, I'm going to get an order of operations error. And then I need to divide again by 60 here. Okay. This will give us our final answer is 8.32 minutes, which will round to just 8.3 because we only have 2 sig figs. So 8.3 minutes is how long it takes for light to travel from the sun to the earth. And that's as it leaves the sun. So, yeah. And then there's a couple of things I can point out here. So we have this a little more clear. On the calculator, like, you can do it in each step, right? So if you wanted to do 9.3 times 10 to the 7th times 1.6093, we could press enter. Okay, that'd be fine. Then we need to multiply it by 10 to the 3rd. So we could write that as 1e to the 3rd. That's another way to write that. Then we want to divide by the value that's on the bottom. So one other way we could do this is using parentheses. So anything that's on the bottom, we could write like this as well. But we need to use parentheses because otherwise it would give us a different value. And then we can divide by 60 to get our same value. So there's a lot of different ways to type this in our calculator and get the same value. I typically do it all in one go. But I've practiced this a lot. So anytime that you're using a calculator and you're doing a division here, so sometimes you'll do this and you're like, oh, wait a second, I got the wrong answer, right? So anything that's on the bottom should be divided. You could also group all these things on the bottom. So you could say, okay, I'm going to group all these on the bottom and multiply on all of them together. And you'll get the same answer as well. So you could group the top numbers, group the bottom numbers. Some people like to just multiply all the top numbers, multiply all the bottom numbers, and then divide the two. I figure that just takes more time. So I'm showing you a couple different ways to do it. All right. I got 2 more examples here for us. These are getting to be slightly more difficult, and chapter 1 goes into a lot of these. So the density of air at sea level is typically given in grams per liter because the densities of gases are very small compared to densities of solids and liquids. And this is the density at 98 degrees Fahrenheit. The volume of the adult human lungs in the expanded state is about 6.0 liters. So we can have 6.0 liters of air in our lungs. And then given that air is about 20% oxygen by mass, what's the number of grams of oxygen in our lungs? Well, we have a density here. This is going to be our conversion factor between grams and liters. And then we have a volume here of 60 liters. And I don't know if, let's see here. So given that air is 20% oxygen by mass, so here only 20% of that air is actually going to be oxygen. So that's a percentage conversion factor that we need to care about here. Let's start with the 6.0 liters. So I always start with a value that's not a compound unit. So compound units like density are always going to be found later on in the dimensional analysis. So we'll start by doing 6.0 liters. And I like to include the substance here that we're talking about. We're talking about, right now, this is the volume of air. Now, I want to convert between the volume of air to the volume of oxygen. And the way I'm going to do that is I'm going to say, well, in 100 parts, so percentage is like this as a part of a whole. So 100 parts of air, there's only 20 parts approximately of oxygen. Let's be a little bit more accurate. Let's look this up. Let's say it's 21. Okay. Okay, cool. So this is going to convert to how many liters of oxygen can be in our lungs at a time. So, okay, let's say here, clear this out, 6 times 21 divided by 100. That's going to say 1.26 liters of air in our lungs is oxygen. Then the next thing we need to do is convert between the volume, because this will give us liters of oxygen, to the grams of oxygen. So we'll start again by figuring out what part we want to put on the denominator. Well, we haven't canceled out liters yet, so we have to put 1 liter on the bottom. When we read this here, we should think 1.20 grams equals 1 liter. Because it's the same thing as saying 1.20 grams per 1 liter. And then we can multiply this through here. And also, another way to do this on your calculator is use the answer key. So answer times 1.2 gives us 1.512. And then we want to round it. So I think we're going to use 2 sig figs here. So 1.5 liters of oxygen. Okay. Oh, that's not right. 1.5 grams of oxygen. And that's a really small amount, right? So 1.5 grams here is it's not very much, right? So that's because the volume of or the density of air is really small, right? So we are definitely going to want to think about that in the sense, like if we go to try to capture that oxygen, it needs to be then captured by hemoglobin in our blood and transported. And if we don't have good exchange of air between our lungs and our body, we're not going to be able to get all that oxygen out. All right, so let's look at the last problem here. This one here is asking about a substance that appears to be gold that has a mass and a volume, and we want to know, is this substance likely pure gold? We can calculate the density. We have a mass and we have a volume. So here we're not really going to make use of dimensional analysis. We're just going to actually make use of the density equation. So density, which is often abbreviated with the Greek letter rho, is equal to the mass divided by the volume. And the mass is typically in grams, and I can write the units like this: grams divided by the volume, and for solids, the volume is typically given in cubic centimeters. And so here I can take my mass here, 465 grams. I can divide it by my volume, 26.5 milliliters. Well, let's see here. So 26.5 milliliters, that's equivalent to 26.5 cubic centimeters. We can see that right here. So 1 milliliter is 1 centimeter, cubic centimeter. Let's see what our value for the density is. It's 17.5. I'm going to use that 3 sig figs here, 17.5 grams per cubic centimeter. So we can write it like that, and then we can take the, if we go back up here, we can take the percentage error here to figure out how much error this is compared to the actual value for gold. So the percent error for this experiment is equal to the experimental value, which is the value we just calculated, 17.5 grams per cubic centimeter. We can subtract the true value, 19.3, and then we can divide by the true value and multiply it by 100. So it's important to know when to use scientific notation, when not to use scientific notation, or sorry, dimensional analysis. So when do you need dimensional analysis, when do you not need dimensional analysis? You won't always need to use it. And so here I want to make sure I use parentheses because I have a subtraction on the numerator, and then we can multiply it by 100. And we get an error of 10%, approximately, negative 9.3. So the negative value, well, I guess I can go out to one more, negative 9.33%. The negative value tells us that our measurement is too low, and this substance that we have here is about 10% less than what we'd expect. So depending on how good our method was, this could be pure gold, but I would say it's likely not to be pure gold. It's likely to be somewhat of a alloy, a mixture of two different metals. Okay, so that's the end of this lesson, and after completing this lesson, you might want to practice some problems in the workbook or in the textbook, and then you can work on the active chemistry problems. The active chemistry assignments are going to require you to show your work using the dimensional analysis that I showed you here. There's a couple tricks to it where you have to think about how to drag these properly. So let me log in and I can show you. So you might get a problem like this, where you have laser pulse has a certain time. It's 2.42 times 10 to the negative second milliseconds, and we want to convert it to a different prefix, nanoseconds. Here you can use method 1 or method 2, where you convert from milliseconds to seconds, and then from seconds to nanoseconds. Or you could convert directly from milliseconds to nanoseconds. There's actually information in here enough where you can do either method. But you'll start with the value. You can always drag from up here your starting values. You're going to always want to start with one of these. And then if we use method 1, we'll convert from milliseconds to seconds. And then we'd convert from seconds to nanoseconds. And then we would write our answer. And our answer will want to be in nanoseconds here. And so we'd want to find our conversion factors. And so, for example, on this one, there's 10 to the negative 3 milliseconds in 1 second. And then for nanoseconds, there's 10 to the negative 9. Where is that at? Here it is. 10 to the negative 9. Oh, I did this wrong, didn't I? Sorry. So this always goes with the base. So in 1 millisecond, there's 10 to the negative 3 seconds. In 1 nanosecond, there's 10 to the negative 9 seconds. And here we can make use of our calculator. You're going to want to make use of your calculator when you do these. 2.42 e to the negative second times 1 e to the negative third divided by 1 e to the negative 9. Something along those lines. And we should get this value. Now, since it's greater than 10 to the third, you're not going to see this answer listed. It will give it in scientific notation, which is 2.42 e to the 4. So that one there. And then when you click it, it'll tell you if you got it right or not. You typically have about 5 tries to get each question. And then, say like for this one, 5 attempts. And most questions are weighted equally. Some problems are worth 2 points. There are some problems that are a little bit harder. And in those ones, it'll be worth maybe 2 points or 3 points. But yeah, feel free to reach out if you have any questions. We're going to have CIC office hours available this summer, so you can get help from tutors in the CIC. And I'll see you in the next lesson, which we'll start covering what the difference between matter, elements, and atoms are. All right, take care.